Welcome to today's lecture. So, we will start off from where we left at the last class. So, remember last class we ended by posing a problem. So, the problem was this, that you are given this reaction, cyclobutene getting transformed to butadiene, right. The activation energy for this reaction is 137 kilojoule per mole as written out here, and the question is, if the temperature is changed from say 420 Kelvin to 430 Kelvin as a 10-degree change, by what factor will the rate of the reaction increase, right? That was the question. So, for this, what the way we approach this problem is very simple. You remember we had derived this equation number 7 in the last class, where what we have is the natural log of K2 over K1, which means the ratio of the two rate constants at two different temperatures is getting related through the activation energy by this relationship. So, what we now do is, if you look at this reaction again, so what do we not, or what do we know? We know what the value of EA is, it has been given to us, it has been provided to us. So, the value of EA is 137 kilojoules per mole, right. We know what R is, the gas constant 8.314 with the appropriate units. Then we know what T1 and T2 are. So, T1 is 420 Kelvin and T2 is 430 Kelvin, right. So, then what we need to find is the ratio K2 by K1, and that will tell you by what factor the rate has changed or increased. Okay. So, let us do this then, let us take this reaction as it is, rather this equation as it is, and plug in our values. Okay. So, based on this, what we have then is, you can write natural log K2 over K1 is equal to EA over R 1 by T1 minus 1 by T2. So, this was the equation. So, now we will start plugging in values. So, K2 by K1 is equal to, so what is the value of our activation energy? It is 137, right, kilojoules, means 10 to the power 3 joules per mole. Now, what about R? So, the value of R is 8.314, then joule per Kelvin per mole, and then I have 1 by T1 minus 1 by T2. So, I can write 1 by 420 Kelvin minus 1 by 430 Kelvin. Okay. So, I will just, since I am moving out, just write it like this. So, it is 1 by 420 Kelvin minus 1 by 430 Kelvin, right, that is what it is. That is T1, this is T2. Okay. So, then natural log of K2 over K1, again I rewrite as 137 times 10 to the power 3 joule per mole, then 8.314 joule per Kelvin per mole or mole inverse, then within brackets I write 430 minus 420 over 420 30. Okay. So, this is what I have, and the unit for this one is Kelvin inverse, right. So, this is Kelvin inverse. Now, it is always good when you are doing any such mathematical calculations to write down the proper units, right. So, you can always keep track of whether you are going in the right direction or whether somewhere you have made a mistake. So, see, this is ln K2 by K1, this would be a pure number, that means dimensionless, no units. So, what are you going to have? So, this joule will cancel out, this mole cancels out, this Kelvin cancels out, right. Hence, we are left with a pure number. Okay. So, when we do the calculations, you check the calculations by yourself, should be getting natural log of K2 over K1 is equal to 0.913, right, and hence you take antilog, what you will get is K2 over K1 is equal to 2.49. This is your answer. So, now what you have seen is that for 10 Kelvin rise in temperature, right, the rate increases by a factor of about 2.5. So, this is a rule of thumb, this is a rule of thumb which says that we call it a general rule of thumb. And what is that? It says that the rate of a reaction will increase by a factor of 2 to 3, that means a factor between 2 to 3 for each 10 K rise in temperature. So, again what is the general rule of thumb? As so, this was the reason this problem was chosen as being discussed, that the rate of a reaction will increase by a factor between 2 to 3 for each 10 K rise in temperature, and you can see this is 2.49, which is well between 2 to 3. Okay. So, with this what we have done is come to the end of a discussion of how rates are affected as a function of or by temperature, and what or how do we how can we have deeper insights into this, insights not only from the Arrhenius equation, but then where the Arrhenius equation originated from, and what are the underlying assumptions in this, and so on, right. So, hopefully again having gone through this discussion of temperature dependence on reaction rates, you would be able to better realize or appreciate what happens when the temperature is increased and how the reaction rate follows that increase in temperature, right. Okay. Now, we move on and come to something which is different, a little bit different. We say we will take a closer look at chemical reactions. Okay. So, what we are saying is that we are going to take a closer look at chemical reactions. Now, when I say that, what do I mean by that? So, what I mean is very simple. What I mean is that suppose you are given a reaction, right. Suppose you are given a reaction where say you have A plus B going to products. So, the reactant is going to products, the reactants between A and B. So, the moment you look at this reaction, what are the different questions that can come to mind, right. What are you trying to achieve? What when you look at a reaction, what do you think about the reaction at your first sight? So, one is that based on this, does the reaction occur in a single step, right, or does it involve multiple steps, right. So, this is an important question you ask yourself. Is it a single step reaction or is it a multiple step reaction? Okay. So, single step means that in one step only A reacts with B to give us P. If it is multiple steps, then it means that it is not happening in one step. So, there is at least two steps, there is at least one step more than the one which is referred to as the single step. So, that means there should be at least two steps to make it a multiple step, right. Next, what happens when a reaction, generally what happens when a reaction goes on to products? You have bonds making, bonds will break, bonds will form, right, during the course of the reaction. That means when the reactants go over to the products. So, your next question is again very simple. So, this is your next question. So, the next question is, which bonds are broken, right? Which bonds are being formed? Not only that, does the bond making, that means bond formation, and bond breaking, does the bond making and bond breaking happen at the same time? So, again, in one question you are asking too many things. So, what are the things you are asking? Which bonds are broken, right? Which bonds are broken? Which bonds are being formed, right? And then, do these two processes, that is bond making and bond breaking, are they happening at the same time? So, see, you are given a reaction, the first question you ask is it a single step or a multi-step process, right? The second question you are asking is, okay, I know that bonds are being formed and also bonds are being broken. Which are those bonds which are being broken? Which are those bonds which are being formed? Are they being broken at the same time? Are they forming at the same time? That means, is the bond breakage and the bond, formation happening together simultaneously? And the other question which you can ask is, also a very relevant question. The other question you can ask is, what energy changes are involved in the reaction or reactions? What energy changes are involved in the reactions? So, the three very important questions, at least three very important questions you ask yourself. A, whether single step or multiple step. 2, which bonds are going to break, which bonds are going to form, will the bond breaking and bond formation be taking place simultaneously? 3, what are the energy changes that are involved as the reaction progresses towards the product side? All these can be summed up in what we say is the reaction mechanism. So, the reaction mechanism will encompass all the informations that you have asked for, that you are looking for, right? Is it a single step? Is it a multiple step? Which bonds are being formed or being broken? Are these processes happening at the same time? Then, what are the energy changes involved? These are the three questions you asked, and these three questions are addressed together by the reaction mechanism of a certain reaction. So, what is the reaction mechanism? So, the reaction mechanism, we can say, so the reaction mechanism is, if I write it again, is providing you something. What is it providing? It is providing you a molecular description. It is providing you a molecular description. It is providing a molecular description of how the reactants are being converted to products. Okay? So, it provides you a molecular description. And please understand that chemistry is all about molecules, and when you are talking about a reaction mechanism, you are trying to understand at the molecular level, that is at molecule by molecule, how each molecule is reacting with the other to give rise to your products. Okay. So, this is why the reaction mechanism is so very important. We can say the reaction mechanism, again if we write, is what? So, the reaction mechanism is a proposal, is a proposed way or path of reactants going to products. So, it is a proposed way of reactants going to products, and that is why. So, that means you are proposing a way based on what? You are proposing a reaction, you are proposing either a single step or multiple steps based on something. So, what is something? Something is the experiments you perform. So, what are the experiments you perform? So, the experiments you perform, so you perform experiments that help you propose the reaction mechanism. So, what are the experiments? It's very simple. So, the experiment means you can say one, you can vary concentrations of reactants, and then the other one is very obvious, can vary temperature, right. So, by doing these experiments, we try to have an insight into how a specific reaction is going from the reactant side to the product side. Okay. That is why the reaction mechanism is so important and is of so fundamental significance in the branch of chemical kinetics, because once you know the reaction mechanism, you essentially know everything about the reaction, as long as the reaction mechanism that you are proposing is a valid one, right. Okay. So, let us start with a few examples, right. So, let us take this first example where we have ethyl bromide aqueous form, okay, reacting with OH minus aqueous form to give you CH3CH2 OH, you know what it is, aqueous form plus Br minus aqueous form. So, let this be our reaction 1. So, we can say that it is very well established that this reaction happens in a single step. That means, in a single step what happens is this molecule reacts with this molecule to give us the products. Such single step reactions, such single step reactions are also known as, this is important, elementary reactions. Okay. So, this is a very important concept in chemical kinetics. So, that means an elementary reaction is what? An elementary reaction is one which proceeds through a single step. There are no other steps involved. One step, it is an elementary reaction. Moreover, if you go back and take a look at this equation, the balanced chemical equation which is out here gives you the message of how the reaction proceeds. So, in this case the balanced chemical equation conveys the one step nature of the process, right. So, again the balanced chemical equation conveys the one step nature of the process. What do you mean by that? You look at this, this is a balanced reaction happening in a single step. Experiments have proved that it is happening in a single step. The balanced chemical equation is telling you, is conveying the message that in one step what happens is, if I go by molecule, a molecule of ethyl bromide reacts with that of hydroxide ion OH minus to give rise to ethanol and bromide. Okay. That is the message that is being conveyed by this balanced chemical equation, and this being a single step, the balanced chemical equation provides you information about how the reaction is going, and hence it is called an elementary reaction. Remember, elementary reaction has to be of a single step, right. That is how an elementary reaction defined. A single step is an elementary reaction, right. Okay. To think about this, I can go ahead and write this, that because the balanced chemical equation is conveying the one step nature of this process, then I can write that R, the rate for this elementary reaction, is given by K times the reactants, which in this case CH3, CH2, Br and OH minus and OH minus. I can straight away write from the equation that I started with. So, because what it is telling is, because it is single step reaction, the balanced chemical equation directly tells me that the rate will depend upon the molecule of ethyl bromide and the molecule of OH minus reacting with each other in a single step, and that is why the rate can be written like this. So, this is something which is very important, right. The balanced chemical equation is conveying the message that this is how the reaction is going, and it also gives rise to something known as molecularity, and I will come to this thing. So, molecularity of a reaction, I will discuss this later, but what it essentially is saying is, if it is a elementary reaction, if the reaction is elementary, then if you look at, so this was the equation, right. If the reaction is elementary, that means happening in a single step, then directly from this this reaction I can write down the rate law, because in a single step the overall order is equal to the molecularity of the reaction. What does it mean? Just keep this in your mind, we will discuss it later again. So, there is one molecule of reactant A, ethyl bromide, reacting with one molecule reactant B, hydroxyl ion, okay, OH minus. How many molecules? One molecule of this, one molecule of this. So, the total molecularity is 2, it is a bimolecular reaction, and if you look at the rate law I have written, what is the total order? This is again 1 plus 1, which is equal to 2, which means in a single step which is elementary in nature, right, obviously elementary single step, then molecularity and order are equal. So, molecularity is equal to order of the reaction, just keep that in mind, it will help our discussion during later times. Now, let us take a very similar reaction, but obviously different reactants. So, I have now C6H5 CH2 Cl in aqueous form plus OH minus aqueous form, giving me C6H5 CH2 OH aqueous plus Cl minus aqueous. So, they let this be reaction 2. All evidence, all experimental evidences suggest that though this is a very similar reaction, you can see, I can show you the reaction again if you remember. So, this was reaction 1, right, this was reaction 1, you see this was reaction 1, this was reaction 1, right, and this is reaction 2. See how similar they are, how similar they are, only now the reactant, the main reactant, principal reactant has been changed from ethyl bromide to this one. Now, once you have this, all evidence tells you that this reaction is not elementary in nature, that means it happens in multiple steps. And what are the steps? The steps are C6H5CH2Cl, right, giving you C6H5CH2 plus Cl minus. Say this is reaction 3. The next step is C6H5CH2 plus OH minus, giving you C6H5CH2OH. This is 4. So, what has happened is, unlike the previous reaction where everything was happening in a single step, this however we see is not happening in a single step. The first step is going like this, where this one decomposes into a benzyl cation and the corresponding chloride, then this cation reacts with the hydroxyl ion to give rise to the corresponding alcohol. So, immediately when you have more than one step, so now what you also see is, before I move on, if I take these two reactions, and if I add these two reactions, right, if I add these two reactions, what will you see? You will see that this cation gets cancelled out from both the sides and you are left with the balanced chemical equation which you started with, right. So, this is an important point of a multi-step reaction, that first, the moment it is a multi-step reaction, then the reaction is not an elementary reaction. Second, when you add these two reactants, these two steps up, or whatever number of steps you have in a non single step reaction, then that should give rise to your balanced chemical equation. Only exceptions being chain equations, which we will not be discussing, but chain equations are very, very complicated in nature, right. Okay. So, what can we say from this? What we can say is that a reaction which proceeds by more than one step is known as a composite reaction or a complex reaction. Okay. It is known as a composite reaction or a complex reaction, and hence the corresponding reaction mechanism is either referred to as a composite reaction mechanism or a composite mechanism or a complex mechanism. That means, I have either a composite mechanism or a complex reaction mechanism. Okay. However, if I go back to this, please note that though this reaction is a composite reaction, it is made up of these two steps, that is more than one step, hence composite or complex, but each step is elementary in nature, each step is elementary in nature. So, what we can say is that a composite reaction or a complex reaction is nothing but a sequence of elementary reactions. There can be 2 elementary reactions, there can be 3 elementary reactions, there can be 4 elementary reactions depending upon the complexity of the reaction, right. So, let me say this again, a composite reaction is one or a complex reaction is one which happens by at least more than one step. The moment that happens, then each such step in a composite reaction is elementary in nature. For example, the first reaction here, reaction 3 is elementary, reaction 4 is elementary. These two different elementary reactions when summed up give us back the complex reaction or the reaction which is happening not in one step, but in multiple steps. Now, this is something very important for you to understand. Okay. So, as I said, so a composite reaction is any reaction where the mechanism would involve would involve at least 2 steps, that means definitely more than one step. Now, in general, so some features you need to keep in mind for a composite reaction. In general, for a composite reaction, for a composite or complex, so composite and complex can be used interchangeably. They kind of tell you they have the same meaning, they tell you the same thing. The number and nature of the steps in the reaction mechanism, which is complex anyway, cannot be deduced from stoichiometry. Okay, cannot be deduced from stoichiometry, right. So, why do we say this? So, let us go back again to the reaction we started with. So, remember, so this was the first reaction we started with, and we said that this is a single step elementary reaction. Look at the stoichiometry, one molecule of this, one molecule of this, and I said that the rate law for this can be written, or the rate expression can be written by K times this concentration of this times the concentration of the other reactant. Okay, and then you go back and take a look at the stoichiometry, you see that, oh, from the stoichiometry I can directly say or write this rate expression for a single step or elementary reaction. That is where the molecularity comes in, and I said the molecular discussed later. But the same thing you cannot do for a complex reaction, you cannot write it down because you just do not know, what the steps are for you to be able to write it down. Okay. So, that is what it meant, or what I meant when I saying, by saying that for a composite reaction the number and nature of the steps cannot be written down. See, if I just tell you that this is a complex reaction or composite reaction without telling you anything else, you do not know whether it is going to go it is definitely going to go through by more than one step, but do not know whether it is going to go through by 2 steps, 3 steps or 4 steps. It will totally depend upon how complicated the reaction is, right. So, for you just looking at the reaction, if you do not know anything about it, you will not be able to say much, except that because it is going by more than one step or through more than one step, it has to be a complex or a composite reaction, that is it. Okay. So, and when we were looking at this reaction, you saw one thing also, this complex reaction is that we were giving rise to a carbocation, this C6H5, the benzyl cation, the carbocation. So, C6H5CH2 plus. So, this C6H5CH2 plus carbocation in this case is referred to as the intermediate, is referred to as the intermediate species or the intermediate in your reaction. So, what is happening? the intermediate. So, intermediate is formed in one step and is being used up in another. Okay. It is being formed in one step and is being used up in another. So, just like this, we go back to the reaction again, you can see it is formed in the elementary reaction 3 and it is being used up in the elementary reaction 4. So, so that is why it is called an intermediate. It is something which is in between the reactants and the products, it appears in between that, it is formed through one elementary step, but it is used up in the next elementary step, so that it does not appear in the final reaction. That is what an intermediate is referred to by. Okay. So, now the other problem is, just so that you know, is when I am saying it is an intermediate, the most logical question that will come to your mind is, can I observe an intermediate? Yes, you can, depending upon how the how stable the intermediate is. In the intermediate stable one, you will be able to observe it during a reaction, okay, by some means. But what happens is, many reaction intermediates are very short lived, it is very hard to observe them, and that is where proposing a reaction mechanism becomes even harder. Because see, if you are going to propose a reaction mechanism, it has to follow the rate expression or the rate law, which we will see later. And to propose that, you need to know what are the possible intermediates that can happen in a reaction. Now, if you are able to see or identify the intermediates by some means or the other, by some technique or the other, then no problem. But if you are not able to identify, then it becomes that much more difficult for you to predict or to propose a plausible reaction mechanism that goes or follows the rate expression. So, this is where the importance of intermediates being able to be identified or not being identified comes into play. So, that is why intermediates play a very important role in many chemical reactions. Okay. And I had already mentioned this to you, that I will not write this down. An important feature of such composite reactions is that if you add up these elementary reactions which make up the composite or complex reaction mechanism, then you should get back the final rate or the final balanced chemical equation which you had started with. The only exception being are chain reactions. So, chain reactions are much more complicated, as I told you. We are not going to do that, we are not going to cover that. But so, in chain reactions you do not expect this to happen, because as I said, the chain reactions are too complicated. Before talking about reaction mechanisms, because that is what we are going for, let us think about the third question that you asked. The third question was this. So, what were the three questions again? Let us try to recall. A, is it a single step? Multiple step. 2, which bonds are being broken? Which bonds are being formed? Are these things happening at the same time, two processes happening at the same time, bond breaking, bond making? The third question is, what are the energies involved? What sort of energy diagram can I plot when I go from the reactant side to the product side? So, let us try to do this energy thing, or energy, look at this energy diagram. So, let us take a very simple plot. I will tell you what the plots are. So, or what the plot is. So, on the horizontal x axis we have something known as the reaction coordinate, right. On the vertical axis or y axis we have potential energy. Okay. So, this is potential energy on the y axis and this is the reaction coordinate. Now, let us talk about a certain reaction. Okay. So, let us talk about an elementary reaction. Let us talk about this elementary reaction. An elementary reaction means an elementary reaction which is a reaction which is happening through a single step. Okay. So, let this be our reactants, let this be our products, and this is typically what you would see being depicted in many books. So, this then would be your reactants and this would be your products. Okay. So, what is this diagram called? So, this diagram is referred to as an energy profile. So, okay. So, I will draw it again later. Energy profile for a chemical reaction, and here for this one we are just considering an elementary reaction, right, a single step reaction. Now, what do you see? You have two things or aspects being plotted. One is the potential energy on the vertical axis and one is the reaction coordinate. Let us try to understand a little bit more what these two mean, these two axes, that means the potential energy axis and the reaction coordinate. Okay. So, let us try to understand the potential energy, the vertical axis. So, the vertical axis is your potential energy axis, right. So, what does it represent? It represents the potential energy. So, what do I mean by that? So, when I say that this vertical axis, which is the potential energy, has contributions from the energy stored in chemical bonds as well as that associated with interactions between each species and the surroundings. Okay. Again, so the vertical axis is what? The vertical axis represents the potential energy, and what is the potential energy composed of? It is composed of the contributions from the energy stored in chemical bonds. So, remember here, so if you have a bond which is being broken and a bond which is being formed, then there is an energy stored within the bond. So, that is what you are looking at, right. Not only that, so then you know, if two reactants are coming and interacting with each other, there is also some interaction energy coming in. So, that will be here. Now, suppose you have ions which are in water or some other neutral molecules which are in water, they would be having their respective interaction energies with the surroundings, which is water, the reactants in water, and else all those energy contributions are being clubbed into this vertical axis, which is your potential energy axis. So, then you know what the vertical axis is. The vertical axis is your potential energy, which is a contribution, which is essentially the sum of the contributions of all the energies that are stored and being changed when the reaction is taking place. That means you go from the reactants to the products. Hence, when I am plotting this potential energy, I am looking at the change in that total energy, which is the total potential energy, as I move from the reaction side to the product side. Okay. Then this leaves me with the horizontal axis, which is the reaction coordinate. What does the reaction coordinate tell me then? Or the horizontal axis, which is my reaction coordinate. Now, the name might be a very fancy name, but it is very simple. So, you see, what does a reaction coordinate try to imply? So, reaction means reaction, coordinate means by looking at some coordinate, some sort like x, y, z coordinates, and looking at some coordinate, you understand how the reaction is progressing. So, that is typically what a reaction coordinate is. So, we can write down, so we can write then the reaction coordinate summarizes the collection of motions such as changes in interatomic distances, right, and bond angles that are directly involved in the formation of products. Okay. So, again what it does, it summarizes, that means it is the collective coordinate of the changes in interatomic distances and or bond angles that are involved, are directly involved as you move from the reactant side to the product side. So, then what does it tell you again? Then it tells you that it represents the path, that the system takes when it moves from the reactant side to the product side. So, I can say then it is the path the system takes as a move from the reactant side to the product side. So, now then having looked at both the axis, the horizontal axis which is the reaction coordinate, and the vertical axis which is representing the potential energy, you will be able to now realize what it means. So, along the reaction coordinate you are having bond breaking, bond angle changing and so on, which bond is breaking, the changes in the atomic distances, and because of those changes, what is happening is your potential energy is changing, because remember the potential energy is a contribution of all those things, right, your bond energy associated with the bond, energy associated with the interactions between the solid molecules, because whenever these changes in bond angles or interatomic distance are happening, all these energies are also changing as we go from the reactants to the products, and this is what the energy profile is telling you. So, energy profile is telling you that as I move along the reaction coordinate, which takes me from the reactant side to the product side, how is my potential energy changing as I move along the reaction coordinate, so that I move to the product side. So, this is the information what the energy profile is giving you, right, when you look at a typical energy profile like this. Okay. Now, as I said, let us discuss this energy profile with respect to a very elementary reaction, I mean respect to an elementary reaction. So, the elementary reaction we were looking at was what? We are looking at CH3 CH2 Br reacting with OH minus, right. So, this is what we are looking at. So, we are looking at CH3 CH2 Br plus OH minus, and this by definition is an elementary reaction. So, now go back to this plot. Let's go back to this plot. So, what are your reactants? Your reactants are these two. What are your products? You know what your products are, right? Your products are CH3 CH2OH plus Br minus, sorry, this is minus, minus 1, I am a minus. Okay. I am not writing the states, you know that. So, what then is telling you is that, so at the reactant side you have what? You have the CH3 CH2 Br and OH minus. At the product side you have the two products CH2 CH2H and Br minus. Now, let us consider or think about the reaction at the molecule level, that is molecule by molecule. So, one molecule of CH3 CH2 Br, say 3CH2 Br, one molecule interacts with one of OH minus. Now, when these two come and interact, so when they are not interacting, so this is your potential energy profile. So, when these two come and interact, what is going to happen is changes are going to happen. See, what are your products? Your products were CH3 CH2H and Br minus, that means the CBr bond has to break and the OH COH bond has to form. So, as the reaction proceeds, you can think like this, as the reaction proceeds you can think like this, that the CBr bond is slowly breaking and the COH bond is being slowly formed. When that is happening, because you have moved from a stable species, that means which this was stable, now because your bond breaking and bond making is taking place, the potential energy is slowly increasing. Why? Because now your bonds have become distorted. The CBr bond before breaking becomes distorted, say it increases in length, say the CBr bond increases in length and finally snaps, right. Then the OH minus, also the COH minus was initially not there, then the COH bond forms and slowly it comes close. So, what you are saying is that as this thing is happening, my potential energy is increasing. It increases to a point up till here where my potential energy is maximum, right. So, that means I have had breaking of bonds and I also have had making of bonds, say taking place to almost equal extent, and when I move there, so when I reach this state or this species, I reach a level which is at the highest point of my potential energy curve or energy profile. So, this is my point, and this point would be referred to as the, so this state would be referred to as the transition state. So, once I reach the transition state, which is the highest point of my energy profile, then more distortion, so it cannot be more distorted than this is my maximum energy. So, a little more distortion would lead me where? Would lead me to the product side. So, this means that now the COH bond is being formed more and more, so that I can go to the product side, and the CBr bond is broken more and more, so that the Br minus comes out, right, and that is how typically a reaction is going to take place. In the next class I will start from here and I will give you another small example, so that it helps you better understand the value of this energy profile, what kind of information does this energy profile have in store for you. Thank you.